Good to see you again. This lecture will give us an introductory view of acid-base reactions. Now, having a firm grasp of this chemistry gives us a foundation for understanding a wide variety of processes. These processes happen in all of chemistry, and especially in biological systems.
Acid-base reactions are, just as they sound, reactions between acids and bases. Typically, these reactions will show little evidence of their presence except for some heat, and gases may evolve in secondary reactions. The key to identifying these reactions is identifying the reactants as acids and bases in the first place, so familiarity with the common acids and bases is invaluable. For now, we're going to limit our acid-base reactions in water solvent. Later, as we continue in our chemical education, we will find that acid-base reactions are prevalent in all sorts of environments and conditions, and definitions of what acids and bases truly are will have to expand. Again, for now, we'll stay in water, and we'll limit our definition of acids and bases to what is commonly known as the Arrhenius definition of acids and bases. Now, there are three fundamental acid-base reactions we will look at on this slide: acids in water, bases in water, and acid-base neutralizations. These are not the only acid-base reactions possible, though. There are many others, such as acid-base gas evolution reactions, but we won't worry about those in this lecture. There will be an interesting acid-base reaction called an autoprotolysis reaction that we will also cover in this lecture. Now let's look at acids and their behavior in water. Following the Arrhenius definition, we identify acids as materials that, when dropped in water, produce a hydronium ion. For instance, if we drop sulfuric acid in water, we produce the hydrogen sulfate or bisulfate anion and the hydronium ion. Notice, this could also be identified as a single displacement type reaction with a single hydrogen ion, a proton, being transferred between the reactants. Now, just as we have strong electrolytes that dissolve and totally dissociate when dropped in water, we also have strong acids that, when dropped in water, will totally dissociate to make an equal molar amount of hydronium ion. Sulfuric acid is one of these. Now, other strong acids to add to this list are hydrochloric acid, HCl, hydrobromic acid, HBr, and hydroiodic acid, HI, nitric acid, HNO3, and perchloric acid, HClO4. Again, these acids, when thrown into water, totally dissociate. Thus, the single arrow left to right is appropriate. Now, a great many other acids not included in this list of 6 strong acids will produce appreciable amounts of hydronium ions, but they quickly come to equilibrium. They do not totally dissociate. One such weak acid is acetic acid, which we also know as the common chemical found in vinegar. Now, let's look at what happens when we put bases in water. We have seen and named a slew of acids, but not many bases. Bases in water produce hydroxide ions. The classic example is when sodium hydroxide is introduced into water. This reaction, as written, could be classified as a decomposition reaction. And as would be expected of any polyatomic ion with sodium, it would be a strong electrolyte and totally dissociates. So this base is considered a strong base, since it totally dissociates and produces a free hydroxide ion in the water. Now, our list of strong bases include hydroxide salts paired with alkali metals and alkaline earth metals, sodium hydroxide, potassium hydroxide, lithium hydroxide, rubidium hydroxide, cesium hydroxide, calcium hydroxide, magnesium hydroxide, strontium hydroxide, and barium hydroxide. Though the last 4 are not as soluble as the alkali bases, but they are very potent all the same. Now, as before, weak bases do not totally dissociate and will come to an equilibrium condition with the reactants. One common example of a weak base is ammonia, which reacts with the water to produce the hydroxide anion and an ammonium cation. Now, if we combine an acid and a base, a neutralization reaction happens, and in water, a double displacement reaction occurs with the products being water and salt. And many times the salt will be soluble, but not always. Now here's an example of a double displacement neutralization reaction between hydrochloric acid and sodium hydroxide. The strong acid and strong base combine to make water and aqueous sodium chloride. Now here's a cute exercise. Let's rewrite this reaction in the complete and net ionic forms. The complete ionic equation is shown. Okay, now take out the spectator ions. Now we obtain the simple net ionic equation of a hydroxide and aqueous hydrogen ion, which is another way to write a hydronium ion, H3O+, combining to make water. Again, remember in acid-base neutralizations in water that the products will be water and a salt. Also, remember to review the common acids and bases. At the very least, the strong acids and bases on this slide are worth remembering. We see that it's straightforward to identify acid-base reactions in water, but one of the practical questions that we might ask is how do we know if a solution is acidic, neutral, or basic, and can we quantify and measure acidity and basicity? Basicity is also known as alkalinity. Now, since the definition of an acid is a substance that produces hydronium ions in water, then the measure of how acidic the solution would be should be directly proportional to the concentration of the hydronium ions in the solution. For a base, it seems natural to calculate the hydroxide ion concentration in determining how basic the solution would be. The complication in water is that both ions, hydronium and hydroxide, are always present. So in water, if the hydronium concentration is greater than the hydroxide concentration in the water, then the solution is considered acidic. And if the hydroxide concentration is greater than the hydronium concentration, the solution is basic. And if the two concentrations are equal, the solution is considered neutral. Calculating the hydronium and hydroxide concentration is often straightforward, especially for strong acids and bases. The typical unit of concentration used in acid-base chemistry is molarity. So let's do a couple of examples. If I had an aqueous 0.015 molar solution of the hydrochloric acid HCl, what would be the hydronium concentration in this solution? Well, we know that hydrochloric acid is one of our 6 strong acids, which means it totally dissociates. Now, what this implies is that for every mole of HCl that is in the water, we know that it produces 1 mole of hydronium ion. In this example, the 0.015 molar solution of the strong acid, HCl, produces an equivalent amount of hydronium, simply a 0.015 molar hydronium ion concentration. Another way to quantify the concentration of hydronium ion is by calculating what is called the pH of the solution. Now, the pH is nothing more than a conversion of hydronium concentration in molarity to a logarithmic scale. Yes, we finally get to use our logarithmic math. The simple formula is pH equals minus log of H3O+, where H3O+ is the concentration of the hydronium ion in the units of molarity. For our HCl example, we know the hydronium concentration is 0.015 molar, so the pH equals minus log of 0.015 and is equal to 1.8239. Now, the number of sig figs in the molarity, 2 in this case, will determine the number of sig figs in the mantissa of the log calculation, so the pH rounds off to 1.82. It shouldn't be a surprise that we can also calculate a quantity called a POH, which would be equivalent to the hydroxide concentration. The equation is POH equals minus log of OH minus, where the OH minus is the concentration of the hydroxide ion in molarity units. So let's say we have a 0.00765 molar solution of the strong base lithium hydroxide, LiOH. We know that it totally dissociates, yielding an equal concentration of hydroxide ions, since for every mole of LiOH in water, we can expect to get 1 mole of hydroxide ion. Thus, the hydroxide concentration will also be 0.00765 molar. Now the pOH will be equal to the minus log of 0.00765, or 2.116338, or after rounding off to the correct sig figs, a pOH equal to 2.116. Just knowing the pH or pOH and nothing else, could we know if the solution is acidic, neutral, or basic? The key to answering this question is knowing a bit more about the solvent water. Water, because of its unique hydrogen bonding and the labile nature of the hydrogen on the molecule, can react with itself in an acid-base equilibrium reaction called an autoprotolysis reaction. In this reaction, water reacts with another water, yielding both a hydronium ion and hydroxide ion. Notice that the reaction is an equilibrium reaction. The free energy delta G of this process is positive for the reaction as written, so only a very small amount of the product will be obtained in this water reaction. For neutral water, the concentration of both the hydronium and hydroxide ion at equilibrium and 25 degrees C is right at 1 × 10 to the minus 7th molar. What a small concentration! Using the pH and pOH equations we defined earlier, these concentrations would yield a pH value of 7 and a pOH value of 7, and answers one of our questions. In water at 25 degrees C, the solution is neutral when the pH or pOH is close to 7. Without going into too much detail, we want to capitalize on a couple of the powerful properties that must be true if the reactions are in equilibrium. No matter what other reaction or compounds are present in the solution, the autoprotolysis water reaction is still present and going on, so it must maintain its equilibrium. The mathematical result of this realization is that the product of the hydronium concentration and the hydroxide concentration must always be a constant. This kind of product is called an equilibrium constant, and for the autoprotolysis of water is denoted as Kw. It's a very powerful equation. If we know the concentration of one of the ions in the equation, we can easily calculate the concentration of the other, no matter what else is in the solution. We can calculate the Kw equilibrium constant from what we know about neutral water. We know that the concentration of both the hydronium and hydroxide ions are equal and are at 1 × 10 to the minus 7th molar at 25 degrees C. So the product of these two numbers gives us the equilibrium constant for the autoprotolysis of water at 25 degrees C as 1 × 10 to the minus 14th. The best thing about a constant is that it's constant. For water and water solutions at 25 degrees C, we can rely on the fact that Kw will always be about 1 × 10 to the minus 14th, no matter what other chemistry is going on. So let's look at how to use this constant utilizing our two previous examples. For the 0.015 molar HCl solution, we know that the hydronium concentration is also 0.015 molar hydronium, giving us a pH value of 1.82. The product of the hydronium and hydroxide concentrations must be 1 × 10 to the minus 14th, which for our purposes we will treat as an exact number for now. So we simply solve for the hydroxide concentration by dividing the Kw value by hydronium concentration, obtaining a hydroxide concentration of 6.7 × 10 to the minus 13th molar. Plugging this concentration into the pOH formula, we get a pOH value of 12.18. This brings us to another useful equation that can be particularly handy in acid-base chemistry. The sum of pOH plus pH will always equal 14 for water at 25 degrees C. The mathematical derivation of this relationship is shown on the slide. We see that it holds true for our example. The pH is 1.82 and the pOH is 12.18, and sure enough, the sum is 14. Now we know that this is an acidic solution because we dropped a strong acid HCl into the water, and we see from this example that for acidic solutions, the hydronium concentration is indeed greater than the hydroxide concentration. But looking at the pH and the pOH values for this acidic solution, we can now state that if the pH is less than 7, the value that we would get for neutral water, or the pOH value is above 7, the value for neutral water, the solution is considered acidic. Now let's look at our base example, the 0.00765 molar lithium hydroxide solution. This solution yields a 0.00765 molar hydroxide concentration and a pOH of 2.116. Now for this case, we will calculate the hydronium concentration in two different ways. First, we can calculate the concentration by simply using the Kw constant. We know the product of the hydroxide and hydronium concentration is equal to 1 × 10 to the minus 14th. After algebraic manipulation, the hydronium concentration will be 1 × 10 to the minus 14th divided by 0.00765 molar, yielding a value of 1.31 × 10 to the minus 12th molar. The second way we can get to the hydronium concentration is to use our new equation, pOH plus pH equals 14. We know the pOH is 2.116, so the pH must be equal to 11.884. Now we know that pH equals minus log of the hydronium concentration, so we can rearrange the equation to solve for the hydronium ion. The result is that the concentration can be obtained by simply taking the antilog of the negative of the pH, or H3O plus concentration equals 10 to the minus pH. A similar equation can be obtained for pOH. Hydroxide concentration equals 10 to the minus pOH. We know the pH is 11.884, so we obtain a hydronium concentration of 1.31 × 10 to the minus 12th molar, just as expected. Obviously, this is a basic solution because we threw a strong base, lithium hydroxide, into the water. For this solution, the hydroxide concentration is indeed greater than the hydronium concentration. Looking at the pH, we see that for this basic solution, the pH value is above 7, and the pOH is less than 7. You will find on this slide a nice graphic that shows the pH values for a bunch of different household products, giving us a sense of the acidic and basic qualities of these materials.
Now, we might come away from this lecture thinking that acid-base chemistry is a very narrow class of reactions, but the Arrhenius water acid-base concepts we focused on in this lecture are only a small part of this family of reactions. There's the Bronsted-Lowry definition of an acid and base, where an acid is any substance that can donate a hydrogen ion, a proton, and a base is any substance that can accept that hydrogen ion, that proton. This broader definition includes the Arrhenius definition, but now allows us to work acid-base reactions in other solvents. And it gets broader. Our friend G.N. Lewis, who gave us the Lewis dot system, he also gave us a more encompassing definition of an acid and base. An acid can be an electron pair acceptor, and a base is an electron pair donor. And now we don't even need a solvent, and we can include a huge swath of chemical reactions that form what we call dative bonds. Now you have a lot of acid-base chemistry out there you can explore. Be well. Catch you later.